It is the second part of section 8.1 as basics of cluster analysis. Here we'll consider various types of clusters: center-based clusters, contiguity-based clusters, density-based clusters, and conceptual clusters. A cluster, by definition, is a set of objects such that an object in a cluster is closer or more similar to every or some of the points in the cluster than any points not in the cluster. That is a basic definition for well-separated clusters. Now let's look at center-based cluster. Then the definition of cluster is changed in this way. A cluster is a set of objects such that an object in a cluster is closer to the center of the cluster than to the center of any other clusters. Along with this definition, center-based clustering algorithm will be designed. Here for the center, we may consider centroid or medoid. The centroid is the average of all points in the cluster, and medoid is most representative point of a cluster. So the medoid is a data point, but centroid is just averaging. So it is made through averaging. Now, these are well separated for center-based clusters. Once it is well separated, then center-based clusters are of more regular shape, because each point will be assigned to the nearest center. So it is distance-based assignment and organization of clusters, so that the shape of clusters are more regular than other type of clusters. Okay, here let's look at contiguity-based clusters. Then the definition of a cluster is given in this way. A cluster is a set of points such that a point in a cluster is closer to one or more other points in the cluster than to any points not in the cluster. So at least one is closer than it will be here assigned as a member of the same cluster. So we have here this one is a cluster, and that is cluster, and again another cluster. Of course, this is cluster, and this cyan region is also a cluster. This whole blue is a cluster, and here another. So there are 1, 2, 3, 4, 5, 6, 7, 8 contiguity-based clusters. So the cluster will be made based on some measure which use the contiguity. Okay. Now this is density-based clusters. Here, a cluster by definition is a dense region of points which is separated by low density regions from other regions of high density. And maybe the background is a low density region, and then these are high density regions. They are separated in this way. So the 1, 2, 3, 4, 5, 6 density-based clusters can be detected. And of course, you have to design the clustering algorithm to detect these the clusters. So based on the type of clusters, the algorithm will be different. Okay. Okay, here we have now conceptual clusters. Points in a cluster share some properties. As you can see here for the left-hand side, now there are two clusters, but on one region, and these points are sharing some property so that it can be shown as a horizontal line segment. And this region has some property such that here now shown in vertical dashes. So like that, each cluster shares some property. So along with that concept, you have to try to find the clusters. So this vision is called conceptual clusters. But sometimes this property will be shared by both sides, so that like over there, here some portion of properties are shared, so that now this intersection belong to both sides. So so that the conceptual clusters are hard to detect, and without this conceptual approach, you cannot get it, and it's not a conventional clustering algorithm. Okay, here most clustering algorithm is defined along with an objective function. So along with the object function, and we try to find the clusters that minimizes or maximize the given object function. If you try to enumerate all possible ways of dividing the points into clusters and evaluate the goodness of each potential set of cluster by using given object function, then the problem is NP hard. I'll explain what it is in the next page. And now the object function can be global or local. For partitional clustering algorithms, usually the object function is global. For hierarchical clustering algorithm, the object function is local. That means that the object function is locally defined, but global object function is usually better. Okay. Okay. Here, this is computational complexity theory. In the theory, there are four types in problem. Here, P-type problem, and P represents the polynomial time. P-type problems are problems which are solvable in polynomial time when running on a deterministic Turing machine. The Turing machine is a theoretical machine. Okay, I explained in here. Okay, English mathematician Turing suggested that, so it is called the Turing machine. Here, okay, in a deterministic Turing machine, the set of rules impose at the most one action to be performed for any given situation. In a non-deterministic Turing machine, you may have a set of rules that describe more than one action for a given situation. So you may ignore this portion anyway. So once solvable in polynomial time, then it's P-type. Now NP is non-deterministic polynomial time. NP-type problem are decision problems which can be verified. So they're verifiable in polynomial time, that is NP-type. Now NP-hard, this one is, okay, these problems are at least as hard as the hardest problem in NP in both solvability and verifiability. NP-complete is the problems which are both NP and NP hard. So here we can summarize. Now NP complete and NP hard, the problems will become more difficult if you go down. Here, verifiable in polynomial time, these three are verifiable, but the problem in here maybe or maybe not. And for solvability in polynomial time, the P is defined as solvable in polynomial time. Now NP is verifiable in polynomial time, so that solvability is yes or no. And these are unknown. Here we have a very famous question. P is NP, so that here the question is P is the same as NP. This question is the most famous problem in computer science, and also here one of the most important questions in the mathematical sciences. The Clay Institute is offering $1 million for the solution to the problem. Here, clearly, P is a subset of NP. So real question is that whether or not NP problems have polynomial solutions. So once you can solve the problem, then you can get $1 million. Okay, we'll continue in the third part. Thank you.